Hi. Okay, this is the video. This is the one that, I don't know, maybe you've been waiting for or maybe not. This is the video where I want to talk about pixels. The pixels themselves. So let's think about this in context for a second. Something that we do a lot in our lives, because this is the lives that we're stuck living, is we draw lines to the screen. We say something like line, 100, comma 50, comma 300, comma 250, and processing says, you have said that I should draw a line. I see the coordinates you want me to draw the line to. I start with here and I end over here and I draw a line there. And the line appears on the screen. But what's really going on here? The existence of this line didn't happen by magic. The line is not something inherent to a computer or a screen. There is an algorithm. Processing has an algorithm. When it gets 2 points, it knows how to fill in all of the pixels between those 2 points to create the illusion of that line on the screen. I don't know if it's really a line or not, but that's a metaphysical question we don't have to answer. This exists because we need to do this stuff all the time. We want to draw lines and circles and rectangles and triangles and put images, all this kind of stuff. We don't want to have to figure out which pixels we need to set, which colors, every single time we want to draw a shape. That's what these functions are doing for us. However, there comes a time in our lives when we might want to do that. We might want to say, these functions are not good enough for me. I have this idea for this kind of shape that doesn't exist anywhere in the world. And I need to set all the pixels individually. Or another scenario might be I took a picture, the picture's too dark, I want to make it brighter, I open up in Photoshop and make it brighter, I save it. That's what Photoshop is for. It's for image processing, changing brightness, contrast, also color, all sorts of things you can do to an image. But if there is something you want to do to an image that isn't available as part of the tools of Photoshop, you need to invent your own image processing algorithm. The way to do that would be by reading the pixels and setting the pixels of an image one by one at a time with your own algorithm, with your own piece of software. And this is what I want to examine how to do in this video, and the next one, and the next one, and I don't know if there's another one after that. So there are a few videos where I want to look at what happens when you can actually just individually set every pixel on the screen. I mean, there's nothing you couldn't draw in theory if you had access to every single pixel on the screen. So that's what I want to look at. Now, there's a kind of quick and dirty way to do this in processing. There are two functions, get and set. And get will retrieve the color of a particular pixel. I want the color at this XY coordinate, and I want to store that in a variable. Set will set a particular pixel to a certain color. Now, these functions are useful, and maybe actually let's demonstrate set really quickly, although in the end what we're going to see is these aren't very efficient, and when we want to actually do something to all of the pixels, then we want to look at the pixel array itself. These are kind of helper functions for just the moment. Here's a scenario where you, and I'll give this to you as an exercise, where you might use get. This is kind of off on a little tangent here, but it's worth it for a second. Let's say you are working on a program where you have a map of the United States. I wish I could think of a different country, but I'm just going to use the United States for right now. And I'm incapable of drawing. I don't know, that's like the worst drawing of the United States ever. But the states are all these misshapen, strange looking things. It's going to be, how do you know when the user has clicked on a certain state, which state the user has clicked on? What if you had a map of the United States where each state was colored with a highly specific color? If you just looked at the pixel underneath the mouse coordinates to see what color that was, you could then know which state the user clicked on. So anyway, this is a kind of cockamamie scenario that we're not looking at right now, though it would be a great topic for a video. But this is why you might want to just retrieve a color of a single pixel. Let's go back and let's look at set for a second. So if I come over here and I have a processing sketch already kind of going here, here's a blank screen, and what I want to do is I want to say, let me set the pixel 300, 200 to the color red. And let me run this, and somewhere in there, can we find it? Is there pause? Everybody pause this video. Okay, I'm back. I found the pixel. So we can see right there, that little pixel is red. We've set that one individual pixel red. So, there's no reason why I couldn't do something like, I don't know, for int x equals 0, x is less than width, x plus plus, set x, comma 200 to red. And look, I now have a line of all those pixels going red across the screen. So we can see how there's a function in processing set which says, for this particular x, for this particular y, stick this particular color in that location. And this will actually work, and we could start to build this example out more and more. But set, there's a detail about set which I will explain in a moment, and we'll come back full circle, which makes calling the set function very, very, very slow. So what we want to do is do this same exact idea, which is a bit simpler, albeit, to see with the set function using the pixel array. And what do I mean by the pixel array? So let's come back over here. So secretly, not really so secretly, but processing is keeping track of, for you, all of the pixels in your window, or as we're going to see in a moment, all of the pixels in a P image. It's keeping track of it in a data structure. That data structure is an array. Just processing is built-in variables. A built-in variable that you are probably quite familiar with is mouse x. Whenever I say mouse x, I get the x coordinate of the mouse. I don't have to declare it. It's just there. It's a variable. I get it for free. There's another variable you get for free. Pixels. Whenever I say pixels, that variable holds all of the pixels, all of the colors on this screen. But what is this data structure? I mean, the window itself, you could think of as a grid. Right? If we were zoomed way in, every single pixel is a square, rectangle, I don't know, you decide. And each one of them has a number. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc., etc., etc. Each one of these is in an array. The pixels are actually an array of integers, or you could think of them as an array of colors. The color data type is really just an integer, the integer that has the red, green, and blue component. This pixel array is one long array of pixels. So if I wanted to set pixel number 9, I could say pixels index 9 equals color 255, 0, 0. This is just like the set function, only I'm accessing the array and a particular index in the array, which is a particular pixel, number 9, referring to a particular pixel that happens to be on the screen. Okay, let's go back and see if we can implement that here. Oh, I'm here. Okay, so let's comment this out, and let's say, right, there's some pixel array. Pixels, index 9 equals color 255, 0, 0. This should work, right? There's no reason why this is going to fail. Let's run this, and look, I got an error. What error did I get? Null pointer exception. Null pointer exception. The pixels were null. There are no pixels. So what's going on here? So something that set did for us is set warned processing in advance, by the way, I'm about to start looking at the pixels. And this is something that you just have to do. Before you access that pixel array, you've got to give processing a warning that you're planning to do that, so it's not just sitting there empty. Processing is going to load those pixels into memory and give you access to them. And the way that we do that is by saying load pixels. So anytime we do an operation with pixels, we need to first call load pixels. By the way, right now I'm speaking about pixels in this sort of general way. Pixels being the pixels of the display window, but soon we're going to start seeing things like image.pixels or image.load pixels. So right now we're talking in generic terms about manipulating the pixels of the display window, but later as we're going to see, it's perhaps a bit more flexible and sometimes more powerful to work with P images and manipulate those pixels which you then draw to the screen. So we'll see that in a little bit. So now that I've done this, this works. Actually, if we searched, I'm pretty sure we would not be able to find a red pixel. Because another thing you need to do, I don't see it in there, another thing you need to do is after you're done with the pixels, you need to tell processing, I am done with the pixels, please update your display accordingly. And the way you do that is with update pixels. So now we can see that I can look into that pixel array, specify a particular pixel, give it a certain color, and call update pixels. And now, I'm not going to pause. Oh, there it is, there it is. There's that red pixel. Pixel number 9, right up there, is red. Beautiful. We have now set a pixel in the window. By the way, this should give you an idea, right? Well, pixel is an array. It must have a length. And why couldn't I write a loop? Why couldn't I write a loop which says, do something to every single pixel in the window? Now I have a fully red window. We just wrote the algorithm for the background function, essentially. Again, why does the background function exist? Because it would be a lot of work to have to put this in our code every single time we wanted to fill the background. It's such a common task. There's a background function. But this here is us doing the background manually. And if you think about this, if I'm setting every pixel individually, there's no reason why every pixel needs to have the same color. You know, random 255, random 50, 200. So now I'm going to set each pixel with some random colors, so we can see I have this kind of purpley, bluey, random set of colors. So this might actually be your first project here, which is our first exercise to think about. You know, this isn't the most, and I want to take this a few steps further. Actually, you know what, I think, but what might be a different way of thinking about this? You know, the first thing I could come up with is just like, I don't know, make some random colors. But what if you wanted to have the colors get like progressively more and more blue as you went across the screen, or all the colors closer to the center be more blue and closer to the edge more red? There are lots and lots of possibilities here. The truth of the matter is, and actually this is why this video can't end here, and has to keep going even though it's we're about 12 minutes in, is that we're missing a really key important piece of information. You could pause now and try to just put this in and try to manipulate this, but there's a real big problem. Like, for example, the exercise I just suggested was have the pixels nearer to the center be more red and the pixels to the edge be more blue. Well, how do I know which pixel is which? I mean, I have this just like numbers. Like this pixel over here is probably like pixel like 722,000. Like, how do I know which pixel is which? I really want to say, I know that I know about its XY, but there's no XY here. So let's return back to our diagram over here, and let's think about something. This is the kind of key piece of information that you're going to see in just about every example we do from now until the end of whenever these videos end. The pixels are in this one-dimensional array, numerically indexed 0, 1, 2, 3, 4, blah, 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 blah. This list of pixels is arranged on the screen in a grid, where the pixels count like this: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. But whenever we work with pixels, we really want to think of them in terms of their x and in terms of their y. Their column number and their row number. Like 0, 1, 2, 3, 4, 5, and the row numbers 0, 1, 2, 3, 4, 5. So I made a 5 by 5 square. This will be nice for making the math kind of work out very nicely. But let's actually, let's pretend that the y was 6, just so we can prove that if I have an image that's 5 by 6, you can't see that. If I have an image that's 5 by 6, how do I figure out where is pixel 4, 3? 4, 3. Now bear with me for a second. Let's count. I'm going to be way too long-winded about this, but let's count. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So this should be pixel 23. It's pretty obvious to us that this is pixel 4. By the way, in my head I just did something wrong, which I wonder if you're doing in your head as well. What's the width of this image? It's not 5 by 6. I wrote that over here. I didn't do it in my head. I wrote it out here, and it was absolutely wrong. The index value is 0, 1, 2, 3, 4, 5, 0, 5, but the width is actually 6, and the height here is actually 7. So this image is a 6 by 7 image. This pixel is pixel number 4. The one below it is pixel number 10. 4 plus the width, 6, is 10. This pixel is actually 16. And then this pixel, I must have counted wrong, should actually be 22. Oh boy, this is such a disaster. 17, 18, 19, 20, 21, 22. I counted wrong. This pixel is definitely 22. How did I get that? we can get, if we know the two-dimensional location of a pixel, it's x and it's y, we can get the one-dimensional location into this array by saying x plus y times width. 4 is the x, y is 3 times the width, which is 6, which is 4 plus 18, which equals, I got a different number. No, that's right. 4 plus 18 is 22. Oh boy. I'm really like, this my mind brain is melting. 4 plus 18 is 22. You know, it seems, maybe I'll re-record this video later. But what's going on here? This is actually quite a crucial algorithm. This magic little formula, you can see why it makes sense. The pixels here, 0, 6, 12, 18. The pixels are internally stored as a long list, but we want to think of them as a two-dimensional grid, an XY grid. So if we're thinking of them as an XY grid, the moment that we need to do something to its color, we need to convert to that one-dimensional index with this formula, x plus y times width. If this is confusing to you, I would suggest pausing this video, draw a grid, number everything, and number all the rows, number all the columns, and try to get this formula to work for you. It'll make itself clear, and otherwise, email me your complaints. I would love to hear them. Okay, so let's go back over here. Now, how do we apply that to this particular algorithm? Instead of looping through all of the pixels from 0 to the length of the pixel array, what I want to do is write an algorithm that loops through every single x value and loops through every single y value. Oops, and this is y plus plus, and this should be x plus plus. Now, I'm almost certain that there was another video earlier which looked at this idea of a nested loop. This is a kind of a difficult thing to get used to, this idea of a nested loop. What I'm saying is, for every single x, when I'm at the first x, go through every y. When I'm at the next x, go through every y. Let's think about that over here. When I'm at the first x equals 0, let me go through every y. Now I'm at the next x equals 1, let me go through every y. Then I'm at the next x, let me go through every y. That algorithm of for every x, look at every y, that will cover every single pixel on the screen. So this algorithm, if I were to say print xy, we're going to just see in the console the coordinates of every single pixel on the screen. But I don't want to do that. I want to say pixels x plus y times width, right? Here I was able to say pixels index I because I was just counting through all the pixels. Now that I'm storing them by x and y, now I have to still look up in the array that one-dimensional index, and this is my formula for it. This formula is now the formula I'm applying right here in the index to the array. So if I were to say this, and I'm going to take load pixels and put it down here, and update pixels and put it down here, and then I'm going to comment out this old way of doing it and save it. Pixels 2, and save it in here. I'll try to figure out where to put these so that you guys can find them. Now I have an entire green window. Again, I've rewritten the background function, but now I have access to every single pixel's XY location. This is very powerful because what if I said y divided by 2, for example? Now you can see the pixels get more and more green as they go down to the bottom. And what if I said in the blue, like x divided by 2? Now we can start to see I'm creating these gradients of color because I can arrange the colors I'm picking according to their x, y values. Let's go ahead and do that distance idea. Let's say I want to get the distance between that particular x, y coordinate and the center of the window. The center of the window being the width divided by 2 and the height divided by 2. What if I set the color equal to that distance? Now look what I have. When that distance is small, I have a black color. When that distance is big, I have a white color. What if I did something random? What if I put this in the draw loop, and instead of having it just be the center, I set the pixels according to their distance from the actual mouse? So there's lots and lots of steps here. This core algorithm of looking through every x and every y and setting every pixel according to that x and y, this is the basis behind every single image processing algorithm. image processing, computer vision, all the things we're going to look, all of the code is always going to have this in it. So this is worth taking some time to get used to. I would say take this, download it, copy it, whatever makes help, and then just try doing it a lot of different ways. Use a sign function, use Perlin noise, use random, anything you can think of as a way of coloring the pixels, give that a try. And try to do as much as you can using those X and Y values. One little improvement though I want to make to this is a little bit awkward, and I think sometimes it can be a little easier to just put that in a separate variable. So I'm going to take that formula, x plus y times width, and put it in a separate variable, and just put that variable in here. I don't know, this to me just gives it a little bit, it's a little easier to read and work with if I'm kind of calculating that and storing it in a variable. And actually, if you look at a lot of the examples that are in processing or certainly in the learning processing book, if you're following along in that, I often use the variable name loc as in like location of the pixel. Okay, so this was a particularly long video, and hopefully it was helpful. That's that. So in the next video, I want to start. This is just kind of start looking at what is it. What right now we're just kind of making up pixels on the fly. But what if we actually read the pixels from an image, manipulate those pixels, and draw them to the screen? That's sort of the next piece that I want to look at. Okay, but I'm going to stop this video and see you in the next one. If I could find the mouse to hit stop recording.